Okay, well, let's get started here. I want to thank you for coming back. It's lecture 3 today. I appreciate you being willing to deal with this online. I'm sitting in Porto, Portugal at the moment. So it's a late night for me because it'll be after midnight. And I was teaching this morning. So I've got 6 hours of lecture to do. All right, so today we're going to be talking about some basic chemical reaction modeling. And we're going to be following Herbert's program pretty closely. Depending on how the time goes, we may skip a little bit of this because some of the material is pretty detailed. As always, I need to remind you that things are being recorded. So today we're going to talk a little bit about chemical reaction kinetics. And as an appendix to this set of lectures, I'm not going to do the slides. There are a set of slides that cover the derivation, the formal derivation of the law of mass action if people are interested. It gets pretty heavy mathematically. And we'll talk about some of the basics of reaction kinetics. Herbert is very interested in stoichiometry. Stoichiometry is quite important when we're dealing with metabolic reactions. It's not so important when you're dealing with signaling and gene regulatory network models. And then, but we're going to cover that since it's something Herbert covers in some detail. And then we're going to talk a little bit about association, dissociation constants, equilibrium, and steady state. And then we'll do some solutions for some simple problems for reversible and irreversible reactions. We'll do a few examples of enzymatic reactions. If you look in a classic mathematical biology textbook like at Britain Essential Mathematical Biology, you'll see solutions of these kinds of problems, analytic solutions doing quasi-steady-state approximation. And so we'll compare those to simulation. I wanted to make a few comments on the homework. I thought people did a generally very impressive job on the homework. I know it was a lot process in a week because it was a lot of reading and a lot of open-ended assignments. And I thought people were quite creative in some of the comparison texts that people found for to compare to Herbert's textbook, and in terms of some of the issues they brought up in terms of what they perceived as being successful or limitations in Herbert's textbook. And I found that quite useful. Some people found some textbooks that I didn't know, which was also very helpful. There wasn't really a right or wrong answer for that first problem, but I was hoping that people would begin to think a little bit about how this kind of modeling works, what is useful. The second problem was everybody did something very interesting. I think that second problem is harder than it looks, perhaps. Maybe not, maybe it felt hard. This question of what is something that's interesting that you can model as a network is challenging. And I think the reason I assigned the problem was really to try to help people begin to challenge themselves and begin to refine their understanding of how you build a network model. And so I think everyone came up with a very interesting example. But in some cases, there were, I'd say, two things that came up. One of which was asking the question, is a network model appropriate or not? And so in some cases, people had great problems, but spatial relationships were very important. Individuals were important. And network models in general, you can certainly do individual models with networks up to a point, but network models tend to be less effective at those kinds of situations where you have specific spatial configurations or reconfiguration of space, and where the individuals are important or they're labeled in some way. Those are the kinds of situations in which agent-based models tend to be more appropriate. And so it's interesting to ask the question, is this actually something that a network model is good at doing? And people, I think, explored that to some extent, depending on the particular problem. The other thing that I think came up, which is also a bit tricky to think about, is what is the state of a node in your model? So if you have, for example, a spatial domain, you're building a model of an ecosystem, and you have some niche in the ecosystem, then the node state might be the population of different species in that node, and, for example, the availability of nutrients in that node. But one has to always think about what the state of the nodes is, because what a network model predicts fundamentally is how the node states change. And so it's important to try to identify what those states are. And that comes actually back to the third problem, which was perhaps should have been given before rather than after problem 2, which was how do you build, well, to read that paper from the Canadian students on the basics of mathematical modeling. And people picked out different aspects of that paper that they found interesting. It was nice. I think everybody had some response to the paper that was interesting. But I wanted to come back to two things that a number of people called out, which I think, personally, I think are very important, and come back a little bit to that problem number 2, which is that it's critical to define your problem aims very carefully. If you're not careful about trying to understand what it is that you're trying to test and explain in detail, and how you're going to validate it, it's very difficult to build a model that's meaningful. And so it's tricky to understand what the hypotheses you're going to test are and how you're going to do that. And I think defining the problem, in a sense, is often the hardest part of building a model. And so coming back to number 2, I think people thought of some great topics, but some people were further along than others in terms of turning those topics into a problem. I think if you read sort of classical articles on how to write a paragraph for an essay, they'll distinguish the topic that you're writing about from the purpose of what you're writing. And I think that in problem 2, some people were further along in going from a topic to a problem than others. And it's not easy to do. And so I think that was interesting. The other thing that some people brought up, which not everybody brought up, which is in the Canadian paper, was the idea that you might build multiple models of the same phenomenon. Those models might differ in hypotheses or might differ in level of detail. And you might then compare the explanatory value of different types of model of the same system. And that's something that we don't always do. And I think that there's a lot of value to that. And of course, if you work very, very hard for a long time to build one model, to then say you have to build a family of models is asking a lot. But I think it's an interesting question to ask whether a single model is sufficient for exploring a system. So I think that some people called that out, and I thought that was very interesting. So I think that this was quite good to see how people responded. For problem 4, my only request is please do remember to submit your code. And ideally, it can be just a screenshot of what the images look like that you got. Because occasionally people wrote, I did this without the code or the images, or they showed an image but didn't show how they got it. And so it's helpful. For problem 4, which is very simple, it's not so critical, but for some of the problems that we're going to face later on, which are more difficult or more complicated, especially if you write code and it doesn't do what you expect, it's very important to have the code submitted. There is always an annoyance using Canvas, in the sense you have to upload the notebook as a separate file. But I do ask you to do that. It's helpful in diagnosing things. So those are my comments on homework 1. In general, I think people put a lot of effort into it. I thought the level of sophistication of the responses was quite high. And given that, I may need to, again, I'm open to suggestions, but my tendency would be to accelerate this class a little bit based on the level of responses in that first homework. People seem to have a fair amount of experience in modeling, and I don't want to bore people. So I hope it may not happen right away. It may take a few weeks for me to work that in. And I'll see how the homeworks are going forward. I think the other thing that came up is that October 25th, I think we were originally scheduled to do a midterm test, partly because I'm going to be traveling. And it looks like Giuliano has arranged for the team that he worked for that does PBPK modeling at Eli Lilly to come and give a lecture for 3 hours about Lilly's work, Eli Lilly's interest in pharmacokinetic modeling. And I think, frankly, it's worth your time. It's much more valuable to you to see how these kinds of models are built and applied and developed in industry than it is to do a test. So I'm not saying we're definitely canceling the little midterm test, but if it's a choice between a test and for you to hear from the horse's mouth about how to apply these things, I think probably it's more valuable to hear how to apply them. If people feel strongly they would like a test instead of that lecture, I can arrange it. So feel free to respond to me. But I thought it was very nice of Giuliano to contact his team that he interned with at Lilly, and to ask them to come down and teach about what they're interested in. So I hope that could be fun. Some semesters I've had an outside lecturer, sometimes not. Depends on the semester, but in general, I think seeing those in different points of view can be quite valuable. So I'm happy for people to let me know how they feel about that. Don't have to do it online. Don't need to put you on the spot. So just reviewing what we did last time, we talked about central dogma of biology, how you go from DNA to RNA to protein. The key point is that there's a lot of spatial organization here and there are a lot of steps. And to just assume that you go from transcription factor to protein directly neglects, if nothing else, a lot of delays in the problem. And also stochasticity. And some people pointed out in their homework problems for number 1, that a gene is typically either being transcribed or not transcribed. And so it's Boolean. And we're typically going to model gene transcription as a continuous function of the concentration of the promoter or the transcription factor. So that brings some interesting questions to bear. We looked at the different main kinds of biological network and how they related, the idea of their interacting and their different timescales. We did a little bit about the questions that one asks and the notation that are used to represent different kinds of networks, metabolic networks, chemical reactions, signaling networks, and the flow of information within cells from the outside of a cell to the inside of a cell. Some of the issues that come up when you have to deal with a notation which is quite compressed for signaling networks. We talked a little bit about motifs. In the context of signaling networks, we talked about complex formation, kinases, phosphorylation, ubiquitination. And one of the things that I think this textbook of Herbert's is not as strong at is motifs. And I think several people noted that Herbert's textbook didn't have the level of detail on motif analysis that, for example, Uri Alon's textbook would have. And so if people have examples of particular circuits that they'd like to see worked up in class and analyzed, I'd be happy to do that. If there's a circuit for compensation, regulation, any circuits that you like, we can work into the class later on. Herbert's textbook really, in this place, is teaching methodologies. He has a couple of circuits, but in general, he's not as strong in this particular textbook in motifs as some of the others. We talked about gene regulatory networks. Again, there's this question about how much of the pathway from promoter all the way down to protein you're going to put in. I often will include that one level of delay through messenger RNA, but in principle, there are multiple delays. And again, there's some ambiguity. There's this nice notation. That notation can hide a lot of complexity, in particular how conflicting signals are reconciled in terms of the control of gene transcription. Here we have motifs again. Multiple control is sitting there as if it's something very benign. It's actually pretty complicated to deal with. The other motifs are pretty well behaved. And again, if people have papers that they find interesting on motifs and they'd like to see some of those worked up and presented in class, I'd be happy to do that. Adam Arkin is famous for his work on motifs. He has some old papers, maybe 20 years old, that do Arkin and Ross has beautiful motif analysis. They were sort of some of the people who coined the terminology of motifs and began to develop those concepts as consistent modules. Mochizuki in Japan has also done beautiful work on that topic. And then we talked a little bit about PK models. They're always going to be the orphans in this class. Herbert doesn't talk about them at all. Just the way he doesn't talk about population models, even though those are network models as well. Some people pointed out that there are a lot of network models of interest in biology that we left out, like neural networks, population network. And as I say, in the previous couple of years, we've taught about disease networks and population models a lot. This year, we're moving back to biochemical networks. Again, the nice thing is the mathematics is the same. And some people also pointed out that Herbert's textbook tends to delay the mathematics. That puts it in chapters 11, 12, and 13. A lot of other textbooks put the mathematics of dynamical systems up front. And ultimately, you need to have that mathematics. I think the question was more who the target audience of the book is. If people have a lot of mathematics, then putting the Ruth Horowitz conditions at the beginning is not going to scare anybody off. If you come from a background where you haven't done so much analytic mathematics, then people may be more comfortable exploring these phenomena of stability numerically before you start doing the analytics. I think Herbert's sitting in a chemical engineering or bioengineering department. Maybe their students there aren't as mathematically inclined, and therefore he takes the modeling first and then the math approach, whereas a classic biology textbook would go the other way. As always, the kind of fundamental thing that we're going to have to deal with in the end is that these things are integrated together. And one of the hardest things we're going to have, if we really want to do anything useful, is actually finding the networks. People talked about Herbert's discussion of these two hybrid methods, which are very, very old. And they don't tell you much about kinetics. They also make a lot of mistakes. And so going from those kind of old these two hybridization experiments to building actually causative models of pathways is hard. And there's still a lot of ambiguity. Metabolic networks, I think, are pretty well mapped at this point after tens of thousands or hundreds of thousands of man-years of effort. But signaling and transcriptional networks are not mapped as well. And there are interesting questions still open there. So finding those resources can be a challenge. And people had no problem typically doing parameter scans, which we did in class last time. So today I want to talk primarily about chemical reactions. We're going to be focusing on chapter 2 in Herbert's book. For backup, I recommend chapters 6 and 15 in physical biology of the cell. The lecture slides that I created, and I'm not going to be showing today on the derivation of mass action, come from Phillips' textbook. Again, the mass action result is extremely simple. The formal derivation of it is reasonably elaborate. So if you're a physical chemist or a physicist, then seeing that derivation can be interesting. Otherwise, it's something that you can probably skip. So what are the kinds of questions that we're going to be asking when we deal with chemical reactions? Well, first thing we typically want to know is what long-term concentrations of our chemical species are. Often you'll have a short-time equilibration or a short-time approach to steady state, and then roughly constant concentrations over a fairly long period of time. Although in biology, almost nothing ever stays constant for very long. So constant is such a relative term. We would like to know how fast concentrations change at the moment under current conditions. That is the rate laws, the rate equations. And then how those long-term concentrations and rates depend on initial concentrations and on the parameters. So that would be what people would call sensitivity analysis. And again, later on in the textbook, we have formal mathematics of sensitivity analysis. To begin with, we're going to treat this as a computational problem rather than mathematical problem. In order to do this, typically in a classical textbook like written Essential Mathematical Biology, you do these things analytically. We did a little bit of that last time, where you set the left-hand side of your equation to 0, say the time to variation is 0, and you try to solve for that. But the first thing we have to do from a reaction diagram is turn it into a differential equation. And so we're going to come back to some of the notation today. And I realize some of this is repetition of what we talked about last time. If people have done this before, it may be repetitive. If people hadn't done this in a systematic way before, seeing it again is probably useful. So again, a chemical reaction diagram takes a substrate on the left and gives you a product on the right. And there's some rate law which sits typically on the arrow. and describes how that reaction happens. Again, notationally, a single arrow indicates an irreversible reaction. A double-headed arrow indicates a reversible reaction. I'll always label the forward and backward rate separately. The forward rate arrow, the reverse on the backward rate arrow. There's a net rate of reaction, which is the difference between the forward and reverse rates. If you write pure ODEs, you write that down immediately. You lose a lot of information when you go to those difference forms because let's switch to a non-biochemical example. If I have a tumor that's growing and I know the net rate of growth of the tumor, that could be because no cells are dying and that cells are dividing at the rate of growth. Or it could be that the cells are actually growing very, very fast and a lot of cells are dying at the same time. Even though the net rate of growth of the tumor is the same, the processes are very different. What is going to happen medically in those cases is very different. And so it is important to know the difference between the forward and backward rates individually and the net. And then the last thing we talked about, did a little bit of in class, was stoichiometry, the idea of mass conservation. Again, if you're doing chemical reactions, you typically write them in mass conserving form. If you do signaling and gene regulatory networks, you typically don't write those in mass conserving form. Although when you do signaling, you mix it. You can usually often mix those two. Herbert spends a lot of time talking about stoichiometry. I'm going to have some stoichiometry in this class, maybe more than we need. Again, because Herbert focuses on chemical reaction networks, stoichiometry is very important. My world tends to be more signaling and in regulatory networks where stoichiometry doesn't apply. But stoichiometric amounts are just the numbers of molecules of a reactant or product used in the reaction. So they're always positive. Typically, they're integers, although sometimes things have odd ratios. So here, 2 ADP goes to ATP plus AMP. The stoichiometric amount of ADP is 2. Stoichiometric amount of ATP and AMP is 1. So we also have a concept of the rate of change, which is that thing that sits on our arrow. And here, the rate of change is not going to be sitting on the arrow. It's the rate of change of a concentration or amount of the species. So it's the slope of concentration or amount. And that itself will depend on the concentrations. And so one of the problems that we have, if we want to put an arrow, a rate on top of that arrow, is we lose 2 molecules of A for every molecule of B. If we put a rate on the arrow, is the rate of the loss of 2 A's, 1 A, or 2 B's? Because there's a numerical conversion factor of 2 to 1. We have to decide what our convention is for that. In addition, we're destroying A and we're creating B. And so we have to decide whether that rate is positive or negative sitting on the arrow. And there's a standard convention for handling this, disambiguating this problem. So the stoichiometric coefficients, relative amount of substance the reaction consumes or produces, that's on either side of the arrow. And then the species stoichiometric coefficient is the difference between the amount on one side and the other. For most chemical reactions, you don't have the same molecule on both sides of the reaction. But there are plenty of situations in which you use up 5 ATPs and you get 2 ATPs back, for example. So it's certainly possible to have the chemical on both sides of the chemical reaction. and you need to take care of that mathematically. So if I have 2A goes to B, the stoichiometric amount of A on the left-hand side is 2. Stoichiometric amount of A on the right-hand side is 0. There's many A. The stoichiometric coefficient is the left-hand side number minus the right-hand side number, minus 2. One reaction destroys 2 A's. The stoichiometric coefficients of the reactants is usually negative. I'm using them up. Stoichiometric coefficient of the products is positive. Again, you can have things on both sides that make things a bit more complicated. Okay. So here's an example. I have 2A plus B going to A plus C. In this case, I have minus 2 on the left for A, and I have 1 on the right for A. And the net stoichiometric coefficient is 1 on the product side, minus 2 on the left-hand side, on the product side, substrate side. And that means one reaction destroys a net 1A, 1 unit of A. Stoichiometric coefficient for B is simple. It only shows up on one side. It's minus 1. And for C, it's plus 1. So to unambiguously label your reactions, the reaction rate, V, is defined as the rate of change normalized with respect to the species stoichiometric coefficients. So if I have A units of A, A's go to B plus BB's go to PQ's, PP's and QQ's. Bad choice of labeling to have lowercase and uppercase letters of the same type. The reaction rate is defined as 1 over the stoichiometric coefficient times the rate of change of the species amount, A dt, B dt, and so on. The advantage of this is we get the same rate for each one, regardless of the stoichiometry. And so now we have a single rate which we can use to label that error. If we're doing gene regulatory networks or signaling networks where we don't have stoichiometry, then none of this matters. But if we're actually doing chemical reactions, we have to keep track of it. And so how do you do this? There's a simple workflow for it. We're going to go through our reactions, and let's just find the first species, A. And we look at the number on either side. We have AS on the left-hand side, AP on the right-hand side. S stands for substrate, P stands for product. So the stoichiometric coefficient is AP minus AC. Actually, it should be AS. I'm sorry, I've got the subscript messed up. AP minus AS. That's CA. And so then the rate of change of A, the amount of A or concentration of A, is CA, that difference in the stoichiometric coefficient, times V. Now we do that systematically for each species. It's not very exciting, but it's impressive to me, if you're not systematic about it, how easy it is to make a mistake. It's pretty easy to get that. Okay. So again, if I have a reaction of form AS goes to AP for A, this change in each species dA by dt is AP minus AS times the V. And so this way I can use the same V for the arrow unambiguously. So let's take some example for this. Suppose I have 4 A's plus B goes to 2 A's plus 3 B's plus C. Well, I have A on both sides. So my stoichiometric, my species stoichiometric coefficient then is 2 on the right-hand side minus 4 minus 2. So the net rate of change of B of A will be minus 2 times V, the velocity of the reaction. For B, I have 3 on the right and 1 on the left. So I have 3 minus 1 plus 2. I create a net plus 2 of B per unit reaction. And so the rate of reaction there is 2 times V. C doesn't occur at all on the left, it only occurs on the right. So my stoichiometric species coefficient is 1, and so the dc by dt is just V. Right? That seems like a lot of real estate to do something very simple, but again, in my experience, it's easy to get confused. So again, if we have multiple reactions, then we have to sum the rates of change for each reaction separately. That could be because our reactions are reversible. We can treat a reversible reaction as 2 independent reactions, both of which are forward. Or we might actually have the same species participating in 2 independent things. ATP binds with almost everything in cells, so it participates in a lot of reactions. And so again, we just systematically go through our reactions. Here, A appears in reaction 1 and reaction 2. We find the stoichiometric coefficient for A in both. We multiply the rate over the first reaction, V1, times that stoichiometric coefficient, species stoichiometric coefficient for V1. And then we do the same thing for V2. And then for the net for A, we just add them up. And antimony will do all of that automatically. It's designed to add up things like that when you write them in the arrow format. And so this is a systematic way then of going from the reaction diagrams that we have at the top to writing a differential equation for how the concentration of A changes in time, how the concentration of B changes in time, and so on. And one has to do this in a rather tedious but systematic way. If you only have 1 or 2 equations, it's not that tedious. If you have lots of them, going through it systematically can be a little bit tricky to just make sure you don't lose any species. So that's, again, why you want to have a systematic approach. So let's do that just as an exercise together. Suppose that we have these 2 sets of reactions. Why don't we just write down the stoichiometric coefficients and the rate of change for the species for these 2 examples. And if you don't really want to go through all, I think the first one we have A, B, C, just 3 species, so that's not so bad. The second one we have A, B, C, D, and E, so you have 5. It's a little tedious. So why don't we just spend a few minutes doing that? So let's look at the first one together. What is the species stoichiometric coefficient for A in number 1?
-4.
-4. So dA by dt would be -4 times V. What about for B?
+2.
+2. So the rate of change for B would be dB by dt is 2 times V. What about C?
+4.
Not so exciting. The second one has a tiny little trick to it. Right, what's the trick? The number 2, what's the rate of change of A?
There is no change. 0.
That's the tiny little trick. That's 0. Okay, now what about B?
So -2 times B1 -2 times B2.
Exactly. Okay, so there's nothing very exciting there. C will be the same, except on the other side. It'll be V1 plus V2. the change of C. And D and E don't have anything funny going on. But the idea was to put in something where something canceled out and something where you had to add between the two. All right. So always we're going to be trying to understand how the rates of change, those V's, depend on the parameters and the variables in the problem. And the key thing that we're going to have to do is come up with rate laws that relate concentrations to the rates of reaction, to the velocities of reaction. In reality, if we're chemists, we're going to consider the rates of reaction dependence on temperature, which is actually pretty important. We might actually try to understand the energetics of the reaction. But in this class, we're going to assume that we don't, that those things are somehow given to us. And they're going to be embodied in a rate constant K. So the first thing that we'll talk about is, suppose we have some mass of a chemical reaction and it's unidirectional. I don't know, I wrote some random thing down where I have some large number of species which come in some complicated structural way. And I made sure that there's an amount of A on both sides and an amount of B on both sides. C and G only appear on one side. Chemical reactions that don't have reaction intermediates are called elementary reactions. And it's extremely unlikely the reaction that's as complicated as what I've written down actually would happen in one step. But mathematically, we're going to assume that that's true for just the purpose of argument today. And the fundamental observation is the law of mass action, which is that for small concentrations, the rate of reaction is proportional to the product of the concentration of each species raised to a power, in particular the power being the stoichiometric coefficient. K is what's called the rate constant, and that rate constant will definitely depend on all sorts of things that mean it's only constant in one particular situation. It'll depend on temperature, certainly it'll depend on pH, it'll depend possibly on whether you're illuminating the system or not, many things. And estimating those Ks is the bane of the existence of anybody doing modeling. Because while you may very well find the pathways that you're looking for, finding those rate constants is usually not easy. And often experimental measurements will differ by factors of 10 or 100 because the measurements were made under different situations and people didn't bother to tell you what they were. Those rate constants are typically hard to measure and are often not known. But these days, people are getting better. Measuring affinities between molecules, binding constants, is relatively easy, but they tell you about equilibrium, not about kinetics. They tell you about the difference between forward and backward rate. Again, if you want the full justification for mass action, it's, as I say, it's given in the appendix to the slide deck. I'm not going to do it today. But the basic idea is, suppose I have a region of space and I want to have my molecules react. And the density of the molecules is proportional to A. And I'm going to assume that reactions are independent in time. And that the probability that the reaction to occur, I have to have all of the molecules are going to react in the same volume at the same time. That's pretty reasonable. Molecules don't interact at a distance. What's less reasonable is how big the box has to be. We don't really have any good way of knowing how big that box has to be. And you could imagine that it's not enough just to be next to each other. You might have to have some particular spatial orientation. So there could be a lot of degrees of freedom to collect. sometimes those things actually make a big difference. What small enough volume is doesn't really make sense. And for a large molecule like DNA, this whole argument falls apart pretty comprehensively. It's not a bad argument for two small molecules. If you want hydrogen and oxygen to react, this is reasonable. ATP to react with something, it's reasonable. DNA, if you want DNA to bind to RNA, spatial orientation is pretty important. And so the whole derivation of mass action is really for small molecules. But probability that we find one molecule in a volume, assuming that the number of molecules, molecular density is low, the probability is proportional to concentration. The probability we find two molecules in that volume goes like the square of the concentration, assuming that the molecules don't take up any space. So if our volume, our reaction volume is large compared to the volume of our physical volume of our molecules, then that's reasonable. And then the probability of having two in that volume goes like the square of the density. On the other hand, suppose that our volume were, our reaction volume were equal to the volume of one molecule. Then no matter how many, what our density of molecules is, we can't have more than one molecule in the same volume because it doesn't fit. And so if there's any excluded volume, all this whole argument falls apart. So we have to assume that this reaction volume, whatever it is big compared to the volume of our molecules. In general, what this means is that as the density goes up, the probability goes up slower than you would expect for a point-like molecule. But our basic mass action observation is we need one molecule in the volume, probability is proportional to concentration. We need two independently, the probability is proportional to the square. If we needed 7, it would be the 7th power. So the reaction 2A plus 3C, we need 2 A's, that's proportional to A squared, and we need 3 C's, it's proportional to C cubed. And we need all 5 of those molecules together. So it's actually the product, A squared times C cubed. And then in the case V of A equals K times C cubed, I've managed to lose the A squared, that should be. One of the things you'll notice is that as the concentrations go up, the rates go up, and they don't saturate. Now, in reality, I can't have an infinite concentration because I can't stuff, I mean, I'm not a black hole, I can't, or a neutron star, I can't stuff an infinite amount of material into a finite volume. On the other hand, for biochemical reactions, the concentrations are typically very low. We're talking about nanomolar, picomolar concentrations. Concentrations are very low. And so in those regimes, you're not limited by the number of molecules you can squeeze into a volume. But you still don't expect that the rates will go up without them. At some point, as you keep increasing the concentration, the rate has to saturate. And so this can't be true when concentrations are low. In general, the rate has to be lower than you would predict. Things are a little bit different when we're talking about the breakdown of a molecule. We've talked a little bit about active breakdown through things like ubiquitination or proteases, where you have a molecule that actually goes in and physically attaches itself to another molecule and cleaves it, destroys it. Here we're talking essentially about what we call spontaneous breakdown. There's a certain probability. Well, the probability for covalent bonding is very, very low. But if you have hydrogen bonds or van der Waals bonds in your molecule, then the thermal fluctuations in the system are comparable in magnitude to the binding energy. And so you can have spontaneous breakdown of molecules. That's pretty common. Dephosphorylation is pretty common that way. But there are other pieces of molecules that break down spontaneously, depending on temperature, pH, the usual thing. But the key thing is that the breakdown of each molecule is independent. Each molecule has some probability per unit time of breaking down. And if I have a series of molecules, they don't influence each other's breakdown. And so the rate of decay is K times S, if S is the concentration of the molecule that's decaying. That's called first order decay kinetics, and it's what we're going to use universally. You'll find a lot of different arguments about rate laws for reactions, but people almost always use first order decay kinetics. It works pretty well. If you have stimulated decay, like ubiquitination, that's different. But if the molecule is just sitting there and breaking down by itself, this is pretty good. And so you'll see that people put a lot of effort into creating the molecule, and they'll assume it breaks down in the first order.
I have a question. How does it relate to the half-life? How we go from one to the other, or the opposite?
So explain to me again what you mean by.
I was thinking if we have the information of the half-life of a particular thing, we just plug in as our K for the substance that we're trying to mimic.
So the bigger the K is, the shorter the lifetime. So K is 1 over the half-life.
1 over, okay.
Actually, there's a conversion factor because K is the time it takes to decay by 1 over E instead of 1/2. So it's the amount of time it takes to decay by 1 over 2.7 instead of 2. But the time constant for the decay is 1 over K. For the decay is 1 over K. A lot of people find it easier to talk about periods than rates. We tend to be better at thinking about this molecule lasts for an hour rather than thinking about its decay rate as 1 per hour. And so a lot of times it's easier to write the rate K as 1 over the lifetime. It's more natural. If you find the rates are good to work out with you in your head, that's fine. But I personally find it easier to say this molecule lasts a week, this molecule lasts an hour, this molecule lasts a minute, and then make my K's 1 over that. Okay. Something that we have to do on the other end is when we're going to create, typically the rate can only depend on the things on the left-hand side of our arrow. The rate only depends on the things that are on the left-hand side of our arrow, although there are possibilities that the product could in fact interfere with the reaction. That would be something additional on our basic structure. And so if I have nothing goes to S, I don't have any way of having my rate change because there isn't anything on the left-hand side of the arrow that I can use to modulate that rate. And so typically, if I have nothing going to S, that's equivalent to assuming there's a constant rate of source for S. And that's called zeroth-order kinetics. The order is the power that appears in the rate law. And S, the concentration of S to the 0 is a constant. There are a number of ways notationally to write that down. Often you'll see well, not often. Occasionally, you'll see the $ symbol used to indicate a fixed value. Suppose that I have a constant external supply of a chemical. That'll be used with a $. And tellurium uses the $ to define boundary conditions. I tend not to. In the old days, when I taught this course, I used that boundary species a lot. These days, I don't tend to use it so much. Again, it shows up in reactions, metabolic reactions more. It's not such a useful concept in signaling and gene regulatory networks. In any case, just the way first order decay gives you exponential decay of the chemical species, zeroth order creation means that the amount you have goes up linearly. Okay. And I realize that's a lot of discussion for a very simple concept. On the other hand, you'll see lots and lots of slide decks devoted to this. I guess people do find it confusing. Okay, so one of the things that you're going to run into is, again, notational problems. If you see an arrow, and the only thing you see on the arrow is lowercase k. In other words, I wrote 3a goes to b, and I write kf on top of it with no a cubed. Mass action is used so much that if somebody writes only the rate constant, you assume mass action. So it's a shorthand. It's a very dangerous shorthand, because what it really should mean is that there's a constant rate of reaction that's independent of the concentration. Since that can't be right, you interpret it as mass action. For boundary species, you have to, because if I have K1 goes to 3a, I have to worry a little bit about what the stoichiometry is going to do. Right? You might expect K1 goes to 3a, following my rules from before, dA by dt would be 3 times K1. If 2b goes to nothing at a rate kb times K2 times b, you might expect that dB by dt is -2, using the stoichiometric rules that I just wrote down. However, what's happening here is that when I write this clustered set of reactions, K1 goes to 3a, and 2b goes to K2 times b. Let's do the decay one first. 2b doesn't decay to nothing. B decays to nothing 1 molecule at a time, because 2b is not a molecular. It's just two independent molecules of B. And so really, if I come down here, where I say the reaction diagram is really a shorthand for nothing goes to A, and 2A goes back and forth to 2B reversibly, B decays. And so when I write that, I do not make the stoichiometric corrections that I've just told you to make. And so when you see a diagram like this one at the top, you have to know that I don't actually multiply the rate of creation of A by 3, and I don't multiply the rate of destruction of B by 2. And again, I'm going into detail about some of these confusions of notation, because when you read an article, you'll see it written the way it's done here. And then you'll see people write equations without the stoichiometry. You say, but why is the stoichiometry different for the arrow in the middle from the ones on the end? And the answer is that those arrows aren't really drawn properly. And so I want to warn you about these things so that when you read articles, I think Herbert now is pretty careful about always being consistent, but in the literature, you'll find people are very sloppy about this, and it's easy to get them wrong.
Yeah, I had a couple of confusions on that specific one in the homework. Because when you say KF A to the third or cube, I didn't know if you were already doing the 3A account for us or if that was the rate. So I basically did it twice, doing the 3 times KF A to the third instead of.
Yeah.
So there was a little bit of confusion there, but I don't know. Then maybe now you can explain to us that if KF A to the third is the final form.
Yeah, so here, the rate of change of A really is -3 KF A cubed.
Okay.
But the
so I
rate
just-
of creation of KA is just K1. So the net would be K1 -3 KF A cubed. And then you'd have to do the reverse reaction.
Mhm.
And again, the convention, which is a good one, is you always divide by the stoichiometry so that everybody sees the same, so that A and B see the same velocity of reaction. The problem is the boundary species at the ends that aren't consistent.
Professor Glazier?
Yeah.
So for this type of notation, because like you first covered this last semester with CompuCell, but mass action is assuming a constant volume for the reactions, right?
Yeah.
So does that cause trouble when we're doing any type of like including like cell growth or changes in the membrane? I guess I'm wondering how often it's appropriate to use this kind of formalism.
Well, so if the cell, I mean, the volumes we're talking about are notional volumes. We're talking about some fiat volume of space. And if the cell is growing, we're bringing new molecules into the cell. The density of molecules isn't changing or isn't changing independently. So that wouldn't be affected there. The place where you might see it would be if I were doing chemical reactions in the gas, and I now expand the gas so that the density goes down. That's a situation which this would make that would happen. But in general, this volume of reaction is something very abstract, and where it comes from and what it means is not really very well understood. Ultimately, the argument in favor of mass action is that it gives you the right answer. For small concentrations, it works. It's not like the Stokes-Einstein relation where there's actually fundamental physics that's derived. Again, there's a little bit of fundamental physics here, and as I say, that if you want to see the 20 slides on it, they're at the end of the But for our purposes, we have to accept it as a phenomenological model. But it's a good question. But typically the growth is happening at a scale larger than the cell of the chemical reaction. So in terms of your little volume distance. Now, if I'm in a membrane and I'm stretching the membrane, then I'm changing the density as I'm doing it. And that will help. Okay. So here was an example again of how to do interpretation. As Joel mentioned, this was a homework problem. We read chapter 2, so this was discussed. So this is essentially a review of the homework. So again, we write nothing goes to 3A, 2B goes to nothing. We interpret that as actually 3 independent reactions. Nothing goes to A goes back and forth to B goes to nothing. And then we can derive it here. K1, minus B, K2B here. And then the stoichiometric forms -3 KFA cubed forward plus 3 KRB squared, 2 KFA cubed. Notice that we have not a balanced equation here, but we destroy 3 A's and we create 2 B's. So there's a 3 in the first one and 2 in the second one for the same species. We create 3 B's, we destroy 2 B's here. So their balance is not symmetric. And it does, when you do this a couple of times, you'll get used to it, but it does take a little practice. It's easy to get it wrong. That's why normally I don't spend a whole lecture on counting 1, 2, 3, 4, 5. But over the years, I've seen people make enough mistakes with this that I think it's probably worth spending a little time on. As they say, several months of programming can save several hours in the library. So this is a bit okay. We talked about the order of reactions, 0th order, 1st order, 2nd order, 3rd order, and so on. For mass action, order is just stoichiometric amount. And when we go to Hill functions, we're going to have a Hill exponent. It's going to come out of thin air, usually, which could be an integer. It's often 4, but could also be something like 2.5. And those are going to be a little bit hard to justify. Okay, so coming back to mass action, and if you look at Paulson, everything he does is mass action. He never does anything that's not mass action. Some of these Voigt tends to do all mass action. People who do metabolic models like mass action a lot because there are simple analytic solutions to things to find the equilibrium. And if you have saturated reactions, you can't solve them that way. Again, as I mentioned before, the key thing is that the probability of that second molecule being in your volume has to be independent of whether your first molecule is there or not. And that means that the molecules have to be small compared to the volume. If the excluded volume is not small, the densities are high, it doesn't work. And so that means that at higher concentrations, the rate of reaction will go up slower than mass action produced. Again, that's not a hard bound. In the case of diffusion, the diffusion constant, Stokes-Einstein is a hard upper bound, the rate of diffusion. You can't do better than Stokes-Einstein. But in this case, it's not a hard upper bound. Okay. If you have 2 molecules that are very different in size, which happens a lot in biology, you have a big globular protein and you're going to attach a tiny phosphate group to it. There are entropic effects, which are called depletion forces, that affect how easily the 2 molecules come together. It's not symmetrical anymore. Getting 2 big molecules together is harder than getting 2 small molecules together. If I have a big molecule near a small molecule, the small molecules tend to want to get next to the big molecule. And so those will have non-mass action effects, and those can be pretty complicated. If I have physical walls, small molecules will preferentially go near walls and push big molecules away from walls. So it's called a depletion force because the concentration of a large molecule will be lower near a wall of a dish than smaller molecules. And that's due to entropy. There are a limited number of ways I can configure a big molecule near a surface. Small molecules don't have the same effect. They have the effect, but it's weak. Cell cytoplasm is really crowded. There are lots of molecules in it. And that can affect the rates of reaction. And that rate of reaction will depend on the size of the molecule. And so that can give some rather unexpected results. In general, all of those things reduce the rates of reaction, but they'll reduce them differently depending on the size of the molecule. It's true that usually mass action is an upper bound, But there are situations, for example, in ions, a lot of molecules have charge, one sort or another. If you have electrostatic attraction or van der Waals attraction between molecules, then you can actually get chemical reactions that occur faster than mass action. Usually not as dramatically as the slowing down, but you can get speed up as well. Again, we're going to neglect all of that chemistry, but if you read the biophysical chemistry textbook, they'll do a lot of complicated derivations. So now we're going to talk about irreversible mass action kinetics. Say A molecules of A, B, B, et cetera, et cetera, et cetera. And the rate law will follow mass action. So it's K times A to the A plus times B to the B and so on. The units, notice there's something that is a little disturbing about writing things this way. The rate constant that I have K, I've called it a rate constant. Notice that the units of K are per time, but it's also going to depend on the particular mass action term I have. A has units of moles or molar. B has units of molar. If A is raised to the fourth power, I have moles to the fourth. If B has units of, if B is raised to the fifth power, I have units of moles to the fifth. A to the fourth times B to the fifth has units of moles to the ninth. And therefore, K is going to have units that compensate for that. And so even though K is written as K all the time, depending on what the particular mass action form is, the units of K will be different. And so you can't look at a K that's given in an experimental text for one reaction and say, well, it should be similar for something else. Because one of them may have units of per mole. One of them may have units of per mole squared. One of them might have units of per mole to the seventh. And so that makes it much harder to compare the meaning of the Ks, the meaning of the rate constants. Okay. But again, let's come back to doing this in a systematic way. Remember that every arrow has only one velocity associated with it. That's the whole point of what we've been doing. So now we have to do what Joel was asking about, which is we're going to multiply our AS, the stoichiometric coefficient of A, gives us A to the A to the AS in the mass action law. And then we have to multiply by the rate law, rate constant K. So the velocity of reaction is K times A to the AS and B times. Actually, I wrote that. I've got that written wrong there. It would be B to the S. BS. So, boy, I've used that slide for years and I didn't catch that. People should help me point it out. I can't pay you, but I can give you some brownie points for correcting my slides. So now let's think about reversible reactions. The rate of the forward reaction depends on what's on the left-hand side. The rate of the reverse reaction depends on what's on the right-hand side. So I'm going to treat this as two separate irreversible reactions. 2A plus B goes to C plus D, and C plus D goes to 2A plus B. So whenever you see a reversible reaction, you automatically break it up into two irreversible reactions. Once I've done that, it's easy enough to write my rate laws. 2A plus B goes to C plus D as a velocity K forward, A squared times B. C plus D goes to 2A plus B as a velocity K reverse times C times D. Note the units of K forward and the units of K reverse are different. That seems funny. We might expect the units to be the same, but they're not. And that means if I do something like take a rate, I can't ask the question, is K forward faster than K reverse? Doesn't make sense because they don't have the same units. I can ask a question about the ratio of them, but notice the ratio of K forward and K reverse has units of moles. This is not something you want. You want these to be dimensionless. And so it means that comparing rates is hard because the units because the rates have units. I don't know if that makes sense to people, but it's actually pretty fundamental problem. We typically say something faster or slower than something else. And if I write 2kf(a) squared times b and krc times d, I can ask which one of those is bigger. But if I just look at kf and kr and say which is bigger, I can't tell you because they have different units. So the total rate of reaction is the difference between the forward and reverse rate. It's easy enough to separate. It's kf times a squared times b minus kr c times d. Notice that you can have the same species on both sides with different exponents because the forward and backward reactions are independent of each other. And we have this problem with the rate constants having different units. So in general, if I have some long string, A times A plus B times B goes to C, E times B times Q plus Q times Q. The net reaction is K forward times A to the A times B to the B times C to the C, so on, minus K reverse, B to the P, Q to the Q, and so on. So I can do that pretty systematically. Here, I don't think I have the typo that I had in the earlier slide. So I look at my equations. The prefactors in my stoichiometry turn into exponents in my rate law. And then to turn it into the rate of change of the species, I have to multiply by AP minus AS, assuming that A shows up on both sides. And so I have each one of these stoichiometric coefficients shows up twice. I have eight. You can see my pointer in the slide. So here, AS, my stoichiometric coefficient on the left. Now I can. AS here shows up in the exponent and it shows up in the prefactor. AP shows up in the exponent on one side and in the prefactor. And so each one of those stoichiometric coefficients shows up twice, once in the exponent on one side of the reaction, either forward or reverse, and then once in the prefactor. And so there is this systematic way of converting the chemical reactions to the ODEs. But it's pretty easy to lose one of these terms when you're doing it. So you do want to be careful. Any questions about that? I realize it's, again, it seems like a lot to be counted, but in my experience, it's easy to get this right. So let's just do an example. I have 2A plus 3A plus 2B goes to 3P. So the forward rate is KF A cubed times B squared. The backward rate is minus KRP cubed. The net stoichiometric coefficient for A is -3. So I multiply that rate by -3 to get the rate of change of A. The same rate applies for B. I have -2 for B, -2. For P, I'm creating 3, so I have +3. In this case, I have 4A plus 2B goes to 3P, and I'm going to compare it to 2a plus 2b goes to 3b. So the only difference is that a shows up 4 times in the first one and 2 times in the second one. For the first one, that means that the forward rate goes like a to the 4th. The backward rate doesn't care, it's the same. Oh, sorry, here I had two. I'm talking myself out in a circle. Let me do that again. I have 4a plus 2b goes to 3p plus 2a. I lost my 2a. And I have 2a plus 2b goes to 3p. Notice that the net reactions are the same. I start out with 4a, I wound up with 2. I have a net loss of 2a's. In this case, I have netted out that a on both sides. Yeah. If I were doing algebra, these would be the same. But as a chemical reaction, the forward rate only depends on the left-hand side. And so B2 is BKF times a to the 4th times b squared minus k right p cubed times a squared. And Ca is minus 2 on both ones. So I get minus 2 times kf a to the 4th b squared minus kr p cubed a squared. If I go to the second one, I get V1 is kf a squared times b squared minus kr p cubed. So I have a different rate law. My velocities are fundamentally different. My prefactors, minus 2, and 3 are the same. So the V is different, but the prefactor is the same. For the first one, I've reversed the order here. For the second one, which I guess I called the first one was here, I have minus 2 in both cases, kf in both cases. Notice the units are different. A squared times b squared, a to the 4th b squared, minus krp cubed, minus kr a squared b to the cubed. So these are very, very different rate laws, even though fundamentally I'm doing the same thing, which is I'm converting 2 a's and getting 3 p's. And so you do have to be careful. Are there any questions about that? Again, I think this isn't complicated, but you do have to be careful. We're used to when we're doing our algebra, we're used to crossing things out. If you have the same thing on both sides of an equation, you get rid of it. Here, if you do that, you get the wrong answer. All right. So let's try doing this. Let's not do all of it, but let's just do one of it. Why don't we do the mass action law for, these are the same ones we had before. Which one would you rather do, 1 or 2? Doesn't take very long. I don't think we want to take that time to do that. Let's do number 1. Okay, so write the mass action rate laws and ODs for number 1. Does somebody want to give me what is the V for, what's the V forward for number 1? Somebody. For mass action.
K forward times a cubed times b to the 4th times c to the 5th.
So that would be the reverse one.
Oh, that's the reverse way. Okay. then it's a to the 7th times b squared times c.
Right. Good. And now if I want to convert it to the rates for A, I have to multiply the forward one by -7 and the backward one by +3. don't remember if I actually have a solution to that there or not. I don't. So let me just put it in the chat. Or does somebody want to put it in the chat for me? We could do that. Somebody come up with the final result for that.
There's also a question in the chat, James.
Okay, thank you. That's a very good question. Somebody says, how do I do long-term concentrations and do the derivation? Yes, exactly. It says if you use A plus B as a constant for mass conserving, so you solve mass conserving reactions and non-mass conserving reactions differently. If you're mass conserving, then the forward and backward reactions give you the same information. And you just solve one of the forward one, and then you use mass conservation. If you have this bit of reaction, the forward and backward ones give you independent information. You solve them separately, and you combine them to get the solution. And I'm going to actually, the next thing I'm going to do is exactly those problems. I'll walk you through. Great. You anticipated my next step exactly. As soon as we're done here. So let me just do this. I'll type it for you. If I make a mistake, you can correct me. So dA by dt is equal to -7 times a to the 7th times b squared times c. That's the forward rate, plus 3 I'm getting this wrong. That's plus 3 times a cubed times b to the 4th times c to the 5th. If I got that wrong, correct. So I'm quite capable of doing it.
Sorry, isn't the EA by dt starting with -4? Isn't the difference between the two? Between the forward and back?
I'm sorry. Yes, thank you. Just, as I say, it's easy to get it wrong. Yeah. So it should be, actually, let me get it right. I got it exactly wrong. It's minus, okay. Oh, hold on. 4, and that is 4, thank you, times the forward one. I need to put the order backwards. The backward one minus the forward one. How about that? Is that right? Can't follow my own instructions.
It's not -4, it's just 4.
I reversed the order so that this is the backward rate. So I'm creating a net 4A with the backward reaction. If I wanted to put them in the order that I have here, I could write it this way. Sorry, I'm getting a lot of this. I could do this if I wanted to write it the way that I had it. The same thing. I multiplied through it by -1. Okay, so as you see, I can screw it up perfectly well. So that's why I have a little cheat sheet for how to do it. And I recommend practicing a bit so that you make mistakes and catch it. Did anybody do number 2? No. Would there be any rate constants in that? Yes. I should definitely have included. I didn't explicitly put a rate constant in here, and that's a good point. I could have a different forward and backward rate constant. So in fact, let me put that in too. So, good point. So you see, I made not one but 2 mistakes, and you caught them. Okay, so we would have K forward here, and we'd have K backwards, K reverse. Is that getting better? We can keep working on it until everybody's satisfied. Better to do that. We'll use a little bit of hive mind to see if we get. Okay, people seem satisfied. All right. As I mentioned before, you'll find that a lot of textbooks assume mass action and write K on the arrow. And so you have to remember to interpret that mass action. You can only see the K. So let's take a few minutes. Let's take a break until 6 o'clock. The people, I assume people want to break even if we're virtual. So why don't we take a short break till 6 o'clock, and then we'll come back to the question that was just asked, which is how do we do chemical equilibria? And we'll basically go over some of the homework problems quickly. Okay, so I'd like to come back to these simple, relatively simple reactions and solving them. I don't know if we'll have time to do all of them, but let's do a couple. These were homework problems. And so again, if you've done them already and you didn't have any problem with them, you can help make sure that the rest of us don't make mistakes. So let's look at this initial one, which is A goes to B reversibly. Under mass action, A goes to B, can have a rate K forward times A. B goes to A, has a rate K reverse times B. No worries about stoichiometric coefficients here, because they have power of 1 on both sides. And no matter what your initial values of A and B are, you're going to get something that looks like this. You're going to get effectively exponential relaxation to a constant value of A and B. So this in here, this is the question. The system is closed, mass conserving. And so we know that the amount of A plus the amount of B is a constant at all times. We'll call the equilibrium value AEQ or A star, or sometimes A infinity for what happens at long times. So there are different notations. People use different notations depending on the world they live in. In this case, we're talking about chemical equilibrium. The reaction stops. Which is not so bad. Say reaction stops is incorrect. Reactions balance. The forward and reverse reactions balance. All right. This one we can solve pretty easily. We can ask the question, what is the amount of B at equilibrium versus the amount of A? What's the ratio? That has a unique value, and that's called the equilibrium constant. And that's written with a capital K. K equilibrium. Okay. So we reach chemical equilibrium when the forward and backward rates are equal to each other. The forward rate is Kf times A, backward rate is Kr times B. So at equilibrium, Kf times A equilibrium equals Kr times B equilibrium. Otherwise, B equilibrium over A equilibrium is K forward over K reverse. So the equilibrium constant is K forward over K reverse. And this is the big problem with rate constants, because measuring K equilibrium is easy. I take my two chemicals, I mix them in a test tube, I let it sit, and I measure the amount of A and B that happen at long times. That gives me K equilibrium. That's easy to measure. The problem is it doesn't give me K forward and K reverse independently of each other. It only tells me the ratio. And all of the flux balance analysis methods that are used for metabolic networks use the K equilibrium and don't use K forward and K reverse because they can't measure. And the problem is that this K equilibrium tells you what the equilibrium concentrations are, but it doesn't tell you about rates. And so if you want to do dynamics, you can't use K equilibrium. So again, in our homework, we said, just did it here, B equilibrium is equal to K forward over K reverse times A equilibrium. Since there was no mass gained or lost, A equilibrium plus B equilibrium was our initial amount of A plus our initial amount of B. So now I can say that A equilibrium plus B equilibrium is equal to A0 plus B0. And now I can substitute in for B equilibrium here. B is replaced by Kf over Kr times A equilibrium. Of A equilibrium plus Kf over Kr equilibrium is equal to my initial amount. I distribute the A out. A times 1 plus Kf over Kr is equal to A naught plus B naught. Divide through by 1 plus Kf over Kr. And I get A equilibrium is equal to Kr over Kf plus Kr times A naught plus B naught. B equilibrium is Kf over Kf plus Kr times A naught over B naught. Notice if I add A equilibrium plus B equilibrium, I get Kr plus Kf over Kr plus Kf, which is 1, times A naught plus B naught, which simply says Ka equilibrium plus B equilibrium is equal to A naught plus B naught. Okay. So in that very simple case, it's easy. If I have a very complicated reversible reaction, A times A plus B times B goes to P times P plus Q times Q. So my forward rate is Kf A to the A times B to the B plus times C to the C. K backwards Kr P to the P Q. Equilibrium constant is still just the ratio of P to the P times Q to the Q and so on over A to the A times B to the B. It's still just Kf over Kr. So the equilibrium constant is the same regardless of how complex things are for mass action. It all behaves as if there are only a single component on either side. And that is a great simplification. And it's why you can do very, very complex metabolic flux balance analysis. One thing we're going to face now, notationally, is that in biochemistry, if I have a chemical reaction, E plus S makes a complex, E goes to F, and E and S combine, not covalently, but through hydrogen bond, van der Waals, ionic bonding. Then it's traditional to write the complex just as ES, like this. And if I'm talking about chemical species, this is unproblematic. The problem is when I talk about concentrations, ES looks like the amount of E times the amount of S, or the concentration of E times the concentration of S. And so you need to have some way of distinguishing. If I write ES like this, is that the amount of E times the amount of S, or the amount of ES? And so classically, you use a dot to say E times S is, and ES means the amount of the compound. Or you put everything in square brackets, square bracket E, square bracket of S, square bracket of ES. So we talked about the equilibrium constant. If I have specifically complex, HA goes to H plus A reversibly, which happens a lot biologically, then the equilibrium constant has a particular form. It's the amount of the concentration of H times the concentration of A divided by the concentration of HA. And that's called the dissociation constant. The reciprocal of that is called the association constant. We don't typically use the association constant. The dissociation constant you'll see a lot. K equilibrium reflects the relative stability of the reactants of the products. If K equilibrium is big, the reactants are less stable than the products. You get a lot of product. If K equilibrium is small, you have a lot of reactant and less product. Now, there's a famous saying that the only chemical equilibrium that matters in biology is death. Organisms, when they're alive, continually take up mass and energy, release it back into the environment. So living organisms are never in chemical equilibrium. Never is a long time, but almost never in chemical equilibrium. On the other hand, it's pretty common to have a steady state where the influx of molecules balances the outflow. And that is a non-conservative situation. And that was the second example we had in the homework. Here I have a steady source of A. A is being converted into B. B is converted back into A, but B decays. And you'll notice that this is asymmetrical because I have zeroth order kinetics on A, the production of A, and I have first order kinetics . And in this case, I get something different. Before, I got two straight lines, flat lines, and the sum of A and B was constant. Here, the sum of A and B is not constant, but I still get eventually a fixed ratio between the amount of A and B. So again, if we have a bunch of species A, B, and C, we say the species is a steady state when the change of concentration of that species is zero on time. The system is at steady state when all the species have a change of zero in time. And it's certainly true that if we're in equilibrium, we're at steady state. But it's not true that if we're at steady state, we're necessarily at chemical equilibrium. Again, the issue here is because in one case, we have no flux. The amount of A and B that we start with is the amount of material that we have at the end. So we have mass conservation. In the example I have here, I have a constant source of A and a loss of AB to first order decay kinetics. The system would be symmetrical if I had a first order sourcing of A or first order decay of B, or zeroth order decay of B, but it's asymmetrical because my source is a constant rate and my decay is first order. And I'll notice that if I look at my time series, the net amount of A plus B starts out at 10, and it winds up somewhere around 3 or 4. But in the end, I still reach a situation where the ratio of A and B is constant. And so I want to know what that ratio is. Okay, so let's do that out. Let's just evaluate A star. And I've skipped some of the derivation here, but we could do that together. I start out by writing, what is dA dt? dA dt is K1 minus KFA plus KRB. What is dB dt? dB dt is KFA minus KRB minus K2B. I now want to know equilibrium, so I set dA by dt equal to 0. I'm sorry, steady state, dA by dt equal to 0, and solve for B in terms of A. I take my second equation and I substitute for B. And now I have an equation that's only for A. And I rearrange. And I get something that looks very similar to what I got before for the equilibrium. I'm going to get the amount of A star is equal to K1 divided by K2. This makes sense because the net amount of material that I have in my system is I'm putting material in at a rate K1, and I'm taking material out at a rate K2 times the amount of material. So the net amount of my material in my system overall is proportional to K1 and inversely proportional to K2. And then what I need to know is how much do I have to modify that by? And this is now given by the following. I have to look at what's happening to B. B has K2 being taken out and KR being taken out. So I have KR plus K2. I have a source, which is KF. The amount of B that I'm going to have will then be KF divided by KR plus K2. Here I want A rather than B, so I have to take the reciprocal. It's KR plus K2 divided by KF. And the net thing is the product. Easier way to do that, perhaps do it in the other order, is what is B star? B star is equal to K1 divided by K2. The only loss in B is from K2. If I then plug in here, I get that K1 over K2, and I have the KR plus K2 over KF. What's the total amount of A star and B star? K1 plus K2 plus K1 over K2 plus times KR plus K2 over KF. What does that do? I get 1 plus KR plus K2 over KF times K1 over K2. I distribute out the K1, K2. A star plus B star is K1 over K2, 1 plus KR plus K2 over KF. This gives me KF over KF. And I get the form K1 over K2, KF plus KR plus K2 divided by K. So now let's compare these two results. This is the driven reaction This is the equilibrated reaction. Notice the core of the reaction is the same. A goes to B goes to A with mass action kinetics. A star has the form K1 over Kf, Kr plus K2 over K2. A equilibrium Kr over Kf plus Kr, A naught plus B naught. B star K1 over K2, as opposed to the more complex form here. Ratio of A star over B star, Kr plus K2 over Kf with the decay, Kr over Kf without the decay. What's a little bit interesting here for A star over B star is there's no K1. The rate of the source doesn't matter. So let's compare these in terms of dependencies. The driven example doesn't depend on the initial concentrations. I don't have A naught and B naught in the first one. The undriven one depends on A naught and B naught. So that's a fundamental difference in the behavior. Changing the initial concentrations doesn't change my final concentrations for the driven one. It does for the conservative one. In the driven example, B star depends only on K1 and K2. It doesn't depend on K forward and K backward, which always seems a little funny. You'd think that it would depend on K forward and K backward, but it doesn't. The undriven one does depend on K forward and K backward. And so the amount of B star that I get is totally different. In the first one, it depends on K1 and K2, which don't even exist in the second one. In the second one, it depends on Kf and Kr. And lastly, if I look at the ratio of the equilibrium amounts, or the steady state amounts of A and B, that has a slightly different form. For the driven one, A star over B star doesn't depend on K1. I can pour stuff in as fast as I like, it doesn't change the ratio. It looks like the undriven one, except that Kr is replaced by Kr plus K2 by the decay. What is Kr plus K2? Kr plus K2 is the rate at which I lose B. B is turned into A at a rate Kr. It's turned into nothing at a rate K2. And so effectively, in the driven one, I have two ways of getting rid of B. And so my Kr is replaced by that sum. And so these are very different systems. The dependencies on the parameters are different. The equilibrium, the steady state values are different, and the steady state and the ratios are different. And so even though that core reaction of reversible reaction is there, the results are quite different. Joel.
I have a question because I'm a little bit confused about B star and B ec. One is equilibrium, right? B ec is equilibrium of B, and B star for steady state. Okay, thank you.
People can be sloppy, and I may be sloppy about that, but they are fundamentally different concepts. Mathematically, they're the same, but biologically and chemically, they're different. In both cases, it means that dA by dt and bb by dt is 0. But what they mean chemically is different. Other questions? Okay. So let's come back to fixed points. A fixed points, that star notation is typical for fixed points. If I have some species, AI, and different species, I'll call it A1, A2, A3, A4, A5. It's easier than, if I want to do summation, it's a lot easier to do that than have called A, B, C, D, E, although for chemical notation, you'd always use the latter. A sub I as a vector is a fixed point of a chemical reaction. If dAI dt is equal to 0, the rates are 0 for all of the A's independently. So a fixed point is a set of concentrations of which the ensemble reaction is steady state. It's possible to have many different chemical concentrations which are equally fixed points. We don't only necessarily have one fixed point for chemical concentration. Mathematically, you get a lot of those. Biologically, it's a little unusual to have more than a couple of fixed points. So we've done an example of conserved moiety already. Conserved moiety is a fancy term for saying that we have some kind of mass conservation going on. And the reason we have to call it conserved moiety rather than just mass conservation is that in our first case where we had A, and A goes to B and B goes to A, we knew that A plus B was conserved. However, if we had 3A plus 3A goes to B, then A plus B wouldn't be conserved. It would be A plus 3B that's conserved. And so conserved moiety means that there is some combination of our concentrations which is conserved, but it doesn't have to just be their linear sum. It could be something more complicated. So for example, if I have an enzyme plus a substrate combining to make enzyme substrate complex, and then enzyme plus substrate going irreversibly to enzyme plus product, the amount of enzyme is conserved. I'm not using enzyme up. I am using substrate up. And so in this case, the amount of enzyme plus the amount of complex, enzyme plus substrate, is a constant. So the total amount of enzyme is conserved. I don't care whether it's free or in the complex. And that's called a conserved moiety. And that is a fancy name for saying not much, but it winds up that the numerical solvers that do the time stepping for integrators will diagonalize the rates and invert them. And if you have conserved moieties, then those rate laws are not invertible, they're singular. And so they diverge. If you're doing forward integration, it's not a problem, but if you try to do implicit integration, it doesn't. And so in the old days, this has been fixed now, but in the old days, libRoadrunner, the numerical solver that we use in Tellurium, didn't automatically handle that. And so if you had something that was like this equation here, where you had a hidden conserved quantity, it would break. And you actually, then Herbert added a flag to tell it to check for that. Now it does that automatically. So let's look at this enzymatic reaction, which I think was another homework problem. So E plus S goes to ES. We have to, again, use those dots to make sure that we can distinguish between E times S and the amount of E, their concentration of E complex ES. So the forward rate is EF times the concentration of E times the concentration of S. The backward rate is KR times the amount of ES. And then we have the ES going at a rate that is R times the concentration of ES, the complex, making E and P. So dE by dt is minus KF E times S plus KR ES plus R ES. ds by dt minus KF E times S plus KR ES. ES dt KF E times S minus KR ES minus RES. So notice that in this case, E and S basically are full balance. RES, RES, KRES, KRES, minus KF E times S, KF E times S. If I add DE, DT, and DES, DT, I get 0. And then the amount of product is just R times ES. Is that okay? So basically, the E equation and the ES equation don't tell us anything new. They tell us the same thing. So let's do that. Let's do a little bit of tellurium to wrap up our evening. So why don't people fire up tellurium and simulate this reaction? And since we haven't done a tellurium, I'm showing, just reminding you the basic syntax for tellurium, which you probably remember. This is not meant to be the reactions you're going to be using, but just to remind you, import tellurium, load the model, run the model. So, see how people are doing now. I have a typo. Right. Oh. Did people get something that looked like that? Anybody?
Yeah, I think a few people gave you thumbs up.
Okay. I'm sorry, because of the way my screen is configured, when I do the screen share, I can't really see, I can't see I've got a single screen, so I can't see the.
Gotcha. Okay, we can announce our thumbs ups.
Okay, great, thank you. Okay, so that's basically what an enzymatic reaction looks like. You notice the amount of substrate decreases continually in time, goes to 0. The amount of product goes up, replaces the amount of substrate. The amount of complex goes up and then goes down again. The amount of free enzyme goes down and then comes back up. Notice that if I add the amount of E and the amount of ES, I have a constant. If I have a lot of substrate compared to the amount of enzyme, what happens? So here's our next exercise. Make the amount of substrate 10 times more. What's going to happen? Somebody tell me. This is called enzyme limited reaction. I have plenty of substrate, but I don't have a lot of enzyme. That happens pretty common. Somebody want to tell me what you got? Are people there? I hope I didn't lose you. You have an internet problem.
You get a big increase in product, and the enzyme and the enzyme system complex kind of approach each other. It looks like at a lower value.
Notice that now the rate at which I get product is increases almost constantly in time. I see a very rapid formation of complex, and then I have an almost constant amount of complex, goes down a little bit as time goes on. The rate of production of product is almost constantly increasing. The rate of decrease of substrate is almost constantly decreasing. If I made this 100 rather than 10, it would be even clearer. Effectively here, the amount of product complex is constant in time after a short equilibration. The rate of increase of product is constant in time. That's called enzyme limited reaction. I can also do what's called the quasi-steady-state reaction, which is very similar. I put my amount of substrate back to 1. And now I make the rate at which my substrate, my complex turns into product very low. So why don't we make, instead of the R, the rate of product production, 1, make it 0.01. What happens then? Somebody try that.
Now you have the S going down and the ES also going down and the product and the E going up.
Okay.
Yeah, if you do on 100, you'll see a displacement bigger than that instead of 10. I was doing 10 too.
But again, you see a continual increase of product, linear increase of product. But in this case, I have a lot of complex compared to the amount of product. You see a very slow decrease in the amount of substrate. So you say, let's run it to 100 instead of 10. See this nice linear increase of product, nice linear decrease of substrate. And here I see the amount of complex goes down a little bit as things go forward. But over short times, almost nothing changes in the amount of substrate. So if I go back to 10, the amount of substrates, complex is essentially constant. The amount of substrates essentially constant. And so here I'm basically just churning out product at a low rate. That's why it's called quasi-steady state. Things are almost flat. Okay. And now I can use that boundary species to try to force a chemical to be constant. That would be, for example, if I have a buffer that forces the amount of something to be constant, or it takes something out of the reaction continually. So let's assume that I actually have truly a constant amount of substrate. And I can do that by putting a $ into my reaction. Here. And let's make S 10 instead of 1 here. And everything else stays the same. What happens? Maybe it's better to do it without the $ first, just with S equal 10. I better make R back to 1.
Now product goes to infinity.
Okay. Here, I have, well, the product better not go to infinity because I don't have, well, sorry, in this first one, the product doesn't go to infinity because I'm going to run out of substrate. If I run it for long enough, I turn all of my substrate into product and the reaction stops. Now I'm going to say that I have a fixed amount of substrate. And I do that by putting a $ here. And let's see what happens.
Is there a way, the same way that we will reference like m.r to change it outside of the core model string, is there a way to change it from outside the model string to being a fixed species, or do we have to change that from within the string?
That's a good question. I don't know the answer.
Okay.
That's an excellent question. I do not know the answer. My guess is that you have to do it by changing the model string. But I don't know. That should be in the antibody documentation. I don't use the boundary species function very often. Again, it's useful. It's very useful in chemical reactions. It's not so useful in signaling and metabolic. I mean, signaling and in regulatory networks. Notice that in principle, I could have put the $ here instead. I could have it multiple times. A single $ freezes the value of S everywhere. On the principle we talked about, that the order of the lines doesn't matter. But as Joel said, if I freeze the amount of S, then I'm going to produce product at a constant rate to infinity. Never run out of substrate. And so now I can compare the case with S locked, the case with S not locked. Early on, it's about the same. As I run out of substrate, of course, things will change.
I got another interesting thing is that S disappear whenever you put it as a constant, right? It doesn't plot. There's no need to plot, but it's interesting to see the color change on the product there. For example, it threw me off for a second.
Yeah, if you make S constant, it treats it as a parameter and it doesn't display it. That's right. The M dot plot doesn't. Good point. And there's actually the comment that Joel, you anticipated it here in number 2. The amount of substrate doesn't change, so the learn doesn't plot it. Okay. As usual, there are some problems with arrows with boundary species. So here's an example that you have 2 different complexes. E can complex with I or with S. If it complexes with I, it doesn't do anything. If it complexes with S, it reacts to form product. Notice that there is no I anywhere in this diagram. You don't see the concentration, you don't see the chemical species I. But you really should have E plus I goes to EI. E plus S goes to ES. Why isn't it written that way? Well, I can't have my E be a target both of EI and ES, because in one case I'm producing E plus S, in the other case I'm producing E plus I. And so I've done some, it's like an apostrophe in English. I've taken 2 chemical reactions that are fundamentally separate. E plus S goes reversibly to ES. E plus I goes reversibly to EI. I've neglected to write the I and the S, and I've glommed the 2 things together. And I realize that that's pretty confusing to look at, but that is the standard notation that you'll run into in the literature. So if you see something that looks like this, you say, where the hell did the S and the I go? You have to know that they're not being written. Interpret it that way. In general, when you see it like this, and you don't see I and S written explicitly, it implies that S and I are being treated as boundary species with constant concentrations. And so that there's just some notation to convert that you have to get used to. I will try to avoid writing those unless I'm explicitly giving you a homework problem where you're supposed to puzzle that. So what does this do? E, what is the rate of change of E? The rate of change of E is dependent on the amount of E. So I lose E in this forward reaction here to ES. I gain E in the backward reaction from ES. I lose E in the forward reaction to EI. I gain E in the backward reaction from EI. And I gain E again when ES breaks down to form E plus B. And so that's dE by dt. And this is a notational peculiarity that you'll run into in the homework. And it's one of those things that we have to get used to, because that's how the world does it. Notice that I've defined a new rate constant, which is Ki prime is Ki times I. Notice the units are different. Because I is assumed to be a boundary species, it's a constant. And so I have Ki times I0, which is a constant. And I'm combining those 2 things into a single constant, K prime. And so the primed rates have different units from what you might expect of it. The last thing is, when you're using tellurium, so far we've always used tellurium to plot all of the variables, but we can select the variables that we want to plot. And the way we do that is we add at the end of our simulate function a list of the things we want to print out. Time is a reserved word and has to be in quotation marks. And then we put in quotation marks the names of the other variables. So here we could put ES. And suppose we make ES a boundary species and we actually want to print a constant. So let's make S a boundary species here. Did I break it? What happened? Won't let me do it. So what happens there? Oh. I typed a period instead of a comma. There we go. I'm only plotting ES and S. Now if I tell it to make it a boundary species, it'll plot S even though S is a constant. So I can explicitly tell it to give me a value of S. So a lot of times, if you have a lot of variables, you may only want to have a few of them. So this will select the ones that you want. Another thing I might want to plot are the rates. So I could plot J1, for example. That'll give me the rate. So that can be that can be useful. Okay. Well, that was the end of what I had prepared for today. We got through 100 slides in a short amount of time, relatively short amount of time. I hope that that was more or less intelligible, despite being a little bit fast. And I have time then for questions or comments. I know there was in the chat a discussion of putting the creating a document to try to do pairing for the projects. And I don't know, do you want to talk about that for a minute before we break? The grants who created the document, a group of me for creating, trying to pair people up for projects. I know I'd created this naive Google Drive document, Google Doc document for that. But if people want to use a more sophisticated one, that would be great. Go ahead.
I was just thinking that maybe if people want to talk about their projects, just very short today, and that can increase the interest of other people trying to work.
So I was going to ask people. In fact, thank you for reminding me. I was going to ask people to present their ideas next week. So I'd asked you to come up with a list of a couple of papers that you might want to work from and submit that today, but not everybody did that on time. And I didn't think it was fair to ask people to present today without warning. But next week, if people could present a little bit, that would be fine. If there's anybody who wants to present for a few minutes today about their ideas, that would be fine too. But I didn't want to put people on the spot about that. So is there anybody who wants to talk a little bit about their ideas today? Maybe to get started. If not, that's fine. I didn't mean to put you on the spot.
Yeah, I think I can talk a little bit about mine. I didn't submit my thing yet, the homework about talking about the project, but if someone is interested, it's very quick. I'm not gonna take half an hour to explain or anything like that. What I've been thinking about doing. Go ahead.
Do you want a screen share or do you just want to talk? It's either way is fine.
Yes, I was not ready for it, so I'm trying to open stuff here. Just give me a second. So what I'm trying to do, I probably can share this screen. Just give me a second. So what I'm trying to work on is the epithelial cell in the cornea. What I was trying to basically do, let's see if I can find it here. Just give me a second. Yeah. So I already wrote a little simple model. I'm just trying to make it go to a steady state, and it's doing it, but I still have to think about a little bit better. I just play around with some equations that I thought, but it's nothing special. So yeah, I'm trying to create, let me see if I can find my paper here. Just give me a second.
Maybe it's worth stepping back and saying what it is you're trying to model. Just
Yeah, let me see if I can find my homework here so I can show that, because I mentioned that in the homework. Yes. So here it is. What I'm trying to show, we're trying to study a little bit about how cornea recovers from a wound, specifically chemical wound, but at this stage we're just saying it's a wound. So the first step that I thought about was to create a steady state of cells being sloughed out and being replaced by other cells. It happens that the system follows this differentiation from a stem cell to basal, and then to wing, and then wings to superficial cells. Since this is not a spatial model, we cannot specifically put them in this space area and say, oh, if you're in this area, you're this type of cell. But basically, that's how it happens. I can show, if anyone is interested, in the future, I can show a little bit more of details. The next step for the model is to introduce some wounds, and depending on the wounds, it will induce some type of cell death. And I want to see if the system will recover from those initial wound events. And moving forward, I want to apply that to a different type of modeling, which is agent-based model. I know that this is not the class, but if you want to do on the fall, you already start a little bit ahead. If you want to jump in with me in this one. I think that is it. I was not ready to present a lot of things, and I think this gives a little bit of an idea of what I'm trying to do. And I also have to think about the future of this, because I am reducing a whole section called the limbus just by saying this is a stem cell. But in there are other cells, and we can also think about how is the mechanism behind on that area. That's another thing that we can introduce to this type of modeling. And, I'm just talking about the very superficial part of the cornea, the epithelial, but there's also the stroma and other elements that compose the cornea eventually. But those are more spatial problems than actually a dynamical population model.
okay, maybe it's worth rolling back just for a second. Thank you for being willing to jump in like that. Maybe it's worth just rolling back a minute. When you have a tissue and you have damage to the tissue and you want to recover the tissue, there's a fundamental problem biologically, which is that somatic cells typically have a finite number of cell divisions that they can go through. And differentiated cells don't divide at all. Terminally differentiated cells don't divide at all. And so the way your body typically fixes things is that they have a population of stem cells, and those stem cells divide. They produce partially differentiated cells, which are called transient amplifying cells, which divide a lot. And then those transient amplifying cells to differentiate into terminally differentiated cells. What you want is to keep the ratio of stem cells, transient amplifying cells, and terminally differentiated cells to be constant, because that will reconstitute the tissue that you started with. The problem is that regulating that is tricky because you have to control the ratios quite accurately. In particular, the number of stem cells is very, very few. So the ratio is small, the number of stem cells divided by the total number of cells. If you lose all of your stem cells, then when the tissue is injured, it can't regenerate. You have degeneration of the tissue, which happens in a lot of degenerative diseases. If the number of stem cells goes up, you produce a tumor and eventually you produce cancer. And so stem cells are a problem because stem cells, on the one hand, are essential. You can't maintain tissues without them. On the other hand, if stem cells get out of regulation, you produce cancer. And so you have to ask the question, what kind of feedback systems are possible between stem cells, they're partially differentiated and terminally differentiated populations, that allow you to have stable control, where you have a stable number of stem cells that's few, these are stochastic models, that's few, but where your stem cells never disappear completely. And so now how that works in space is a whole other set of questions. Here he's talking about that. But the fundamental question about how do you build feedback loops that give you stable numbers of fractional stem cells is pretty fundamental. There's this nice paper by Natalia Komarova that looks at every possible regulatory circuit you could have, all of the combinatorics, every possible combination, and asks the question, which ones of those are stable and which aren't stable? The answer is there are only a couple of all the possible motifs that are conceivable, of which there are quite a few. There are only two that could possibly work. And that's actually very nice because it's a very abstract mathematical model that gives you something very fundamental about what's possible in biology. That doesn't happen that often.
Yeah. Yeah, I still have to develop a lot on this. I didn't have enough time to think about everything, but if anyone wants to jump in this project, I will also appreciate.
So again, there are no rules. People can work on their own. People can team up. I encourage you to team up because these projects are a lot of work and people learn from each other. But I don't want to force people to work on things they're not interested in. I would ask you for next time to try maybe prepare 1 or 2 slides. Even if you're not at the point of having a project yet, if you read a paper or 2 that were interesting, that you handed in this week, you just want to tell us about them, that would be great. Is that reasonable? It's not going to be part of the formal homework. I guess I can add it as a homework assignment. Would be to prepare, and it's not your formal pre-proposal for the project. This is more exploratory, right? Get interest from your colleagues. 5 minutes. All right. Okay, I should be back next Monday, and I will be. I'll try to be available, but the next couple of days are going to be quite busy for me. And so if I'm out of contact, I'm not trying to ignore you, but it's just this conference is going to be quite dramatic next 2 days. Okay, well, I thank everybody for coming today. I hope the internet or online format wasn't too much of a problem for people. And I'll look forward to seeing you next week. Good night.
Night.
Have a good trip.